Hello. So, good morning, students. So, today we will start our third tutorial. So, tutorial 3, thermodynamics. Okay, so one second. Mm, mm, Hello. Okay, so let's start from our first problem. Okay, so the problem number one. So, mm, so this tutorial is mostly focused on phase transition, triple point, gives free energy, okay, and van der Waals pressure, van der Waals gas pressure, and all those things. So these kind of topics will be covered during this today's tutorial. Okay, so so let's start from the first problem. So mm, the vapor pressure of a solid selenium is given by log P millimeter is equal to -7440 by T plus 12.28. So here T is basically is the temperature of the vapor, okay, and this is the vapor pressure of a solid selenium, okay. I mean, in this case the state of the selenium will be solid, okay, and liquid selenium by log E equal to 5390 by T plus 8.63. So basically the vapor pressure of the selenium in solid state is given by uh, this expression, and for liquid case the vapor pressure is given by this expression. Now so these basically are the two vapor pressure at different states, okay. Now you have been asked to find out the triple point temperature, that is in degree centigrade, of selenium is, okay. So so vapor pressure at solid state and liquid state is given here. Now with this information in our hand, we have to calculate the triple point temperature of the selenium. So before solving this problem, so let me just briefly discuss what is basically triple point of a state means, okay. So in thermodynamics, the triple point of a substance is basically the temperature T T trip, we can say T trip, uh, and pressure also. I mean, both the pressure and temperature will be involved here. I mean, to obtain this triple point of a substance, so you have to have a specific triple point temperature and triple point pressure in order to attain this triple point state of any substance. Okay, so P trip at which the three phases three phases means gas, liquid and solid of that substance coexist in thermodynamic equilibrium. Okay, so this is basically the uh, definition of a triple point. So basically what does that mean? So basically at a particular temperature and particular pressure, all the three states of a substance, that is the gas state, the liquid state and the vapor state, all these three states uh, coexist at the same time. Okay, so let me just demonstrate with a diagram, then maybe you will able to understand much more clear way. So let's suppose this is the axis. So this is basically will be a schematic diagram, okay, representative diagram. So here pressure, y-axis is the pressure and x-axis is the temperature. T and pressure. So let's suppose this is the line. So these three states, let's suppose this area denotes liquid phase of a substance, this area denotes vapor state or gas phase, and this basically solid phase. This boundary line, one second, so this boundary line basically is the critical line between two different states, solid state and liquid state. Similarly, this line is between liquid state and vapor state, and this line separates the substance from solid state to vapor state. So these are basically the transition lines, okay, between three states. Now this is basically a schematic diagram. Okay, now here the triple point, like in this diagram, the triple point will be this point. Okay, this point will be called as triple point. The reason is because at this point all this state, the like here the liquid state, the vapor state and also the solid state, both these three states basically coexist in this point, so that's why it's called a triple point. Okay, okay, so now okay, so this is basically the definition of a triple point of the state. So now we'll come back to our question. Now in our question we have already made the pressure, vapor pressure of two state is given by the triple point temperature we have to calculate. So we know, let me first write this expression. So at solid state, at solid it's log P equal to -7440 by T plus 12.78, and at liquid log P will be equal to -5390 by T plus 8.63. Now as you can see, so in this triple point you can see both this solid, that means this is between solid and liquid state. Okay, so in this triple point, as the solid state and liquid state coexist at the same at the same time, so that means the pressure at solid state should equal to the pressure at liquid state, and that pressure should be equal to the critical, I mean the triple point pressure, right? So in this case, so pressure, so this so that means that this log P of this pressure at solid, that means this one, and the log P liquid would be equal to log P uh, triple point, right? Because if P solid, basically P solid, P liquid and P triple are equal, so if these three things are equal, if you take log of them, the log should be also equal, right? So basically we can then write it like this, so that means that from this relation we can write it like this, right? So -7, basically you are substituting this log P solid value here and log P liquid value here. After substituting this, we are getting -7440 by T plus 12.78 equal to -5390 by T plus 8.63. So these two things are basically equal, and at P triple point the temperature will be also T triple point, right? So this temperature will be also T triple point, this is also be T triple point. Okay, now this temperature you have to actually calculate. So I have not I have to forgot actually written the options actually. Okay, so let me also write the options. These are the options. So option A was 267.83, option B was 347.67, option C was 493.98, and option D was 220.98. So all of this in written is degree centigrade. So this, so triple point temperature you have to calculate, that means this temperature you have to calculate. So now just normally you have to solve this equation. So now we will take this term in left hand side, so sorry, this term in so -7440 by T plus 5390 by T equal to 8.63 minus 12.78. Now this basically gives you -7440 plus 5390 by T equal to -4.15. If you do the subtraction, it will give you 2050 by T into T by T equal to -4.15, and from there T will be equal to 2050 by 4.15, so there should be a minus, and a minus will cancel, and T basically gives you so the option was 22. So basically if you calculate 2, so T basically gives you around 220.45 Kelvin. That basically approximately gives you this answer, right? This option D. Okay, option D. So in this case option D will be the correct answer. Okay. So let me just tell the whole process once again. So this is the question. Okay, so the vapor pressure of a solid selenium is given by this, and same selenium in liquid phase, the pressure is given by this. Now you have been asked to find out the triple point temperature of the selenium. Okay. Now we know triple point actually basically is a point, I mean the for a particular value of a temperature and pressure, that is basically denotes the triple point in pressure temperature scale. So at that particular pressure and temperature, all the three phases of a substance, that means the liquid phase, the solid phase and gas phase, all these three phase coexist with each other. You can see from this schematic diagram, see all the solid, liquid and vapor phase, all these three are coexist in this triple point. Okay, this is basically the definition of triple point. So So as like the pressure, that means in our problem it's like this for selenium, solid and liquid is pressure is given. So if these two states are coexist at the same time at triple point, so that means their pressure should be similar, right? So P solid and P liquid will be similar, equal to each other. That will be equal to the pre triple point pressure. So if these two are equal, then the log should be equal, right? So this, now we have just substitute the have substitute the expression of the log of the pressure here, and after doing the substitution we have done the calculation, and here basically T will gives you the triple point temperature, right? So if you solve this, all these things, all the steps, you will get the triple point temperature for the selenium gas, selenium substance, okay, like where both the solid and liquid phase will coexist, okay. And this, so for our like this problem, the option D was the correct option, okay. So this is the problem. I hope you understood how to approach the system, okay. So now, okay, so this is it. So option, so question 2. Check. Hmm. Now come the question 2. So question 2 is, the fugacity, I will discuss what this fugacity means actually, of NH3 gas, the B value. So B value basically means here that the, that you have learned in the Van der Waals gas equation, right? There was a term and there is a B term, which accounts for the like one is like volume correction and one is the volume correction and pressure correction. So those two in those two correction term, there were two constants are involved, right? One of the constant is termed as A and second constant is termed as B, right? So basically here NH3 gas, we have to consider it as a Van der Waals gas, okay. And for that Van der Waals gas, the A value is not mentioned actually, but the B value is mentioned, so we have to consider it, okay. So B value is given as this 3.707 into 10 to the power minus 2 liter mole inverse at 25 degrees centigrade. Now having true pressure of 10 atm is, okay. So these are the, so we have to calculate the true pressure, okay. It's important thing, important term. 10.153, B is 11.00, option C is 15.67, option D is 9.87, okay. So now the thing is, so so in the problem, So let me first explain what is fugacity is. So basically fugacity is basically is a thermodynamic property that essentially represents the effective pressure of a real gas or or in a mixture of gas. Okay. So um, so what does that means? Okay, just 1 second. So basically for ideal gases the gas equation is like this: PV equal to nRT, where P's expression is given like this: PV equal to nRT by V, and this is basically the true pressure of an ideal gas. Okay, now the thing is but here it's here you have to consider like the van der Waals gas, right, which is basically a real gas, not ideal gas. So for real gas we have to we have to take some assumptions, right, but like for ideal gas, we didn't consider some things like uh, the force, the pressure that has been exhibited by the molecules, like each constituent molecules of ideal gas, that we will consider for the real gas, right. And secondly, the size of the molecule also not considered in case of ideal gas, right. So for real gas we actually consider all of these assumptions, right, which we didn't consider in case of a ideal gas. So if we consider this, the equation would be, can be for a real gas can be written like this, right, P plus A by V square into V by minus V equal to RT. So this term basically holds because of the correction in the force, because the gas molecules itself has some velocity, so because of that it will exert some forces on the like on its surroundings. So that thing is not considered in actual, like in the ideal gas case, but we have to consider in real gas case. So for that this correction term in pressure comes. And similarly for ideal gas case we consider this size of the molecule as in gas molecule as a point size, but for real gas we have to consider that uh, there is a like a considerable radius, I mean considerable size of the molecule exists. So for that there is a correction term in the volume term also. So if you consider both of these corrections, this will be the final equation of state you will be getting, and this equation of state is basically known as van der Waals gas equation, right, van der Waals gas equation. Okay. Okay. Hmm. Now when you consider all of these things, okay, like this correction of the pressure terms, so if you consider those two things, okay, so basically now so now uh, F is basically the that corrected effective pressure, that means after the correction what is the pressure value of the pressure. So that thing is basically represented by this fugacity thing. Okay, so fugacity is the is basically written as F actually. So and this F is related to the pressure of an ideal gas by a constant dimensionless constant phi. So F is equal to basically phi into P, where P is the pressure of ideal gas. Okay, this phi is actually basically known as coefficient of, I mean, fugacity coefficient. Okay, so phi is a coefficient of fugacity coefficient. So for ideal gas case, for ideal gas case, the value of phi should be equal to 1. Okay, so this is basically the fugacity is defined like this, and this basically is the effective pressure of the fugacity. Okay, so let me write F is the effective pressure or the fugacity. Okay. Now so this is one relation. Now this phi, there is a relation. Okay, let me write the relation. So the phi is related with this coefficient. Okay, so this uh, coefficient of van der Waals coefficient, gas coefficient that comes, this is this B coefficient. Okay, that means that coefficient that comes in the volume correction terms in this way. Okay, so let me write it like this. So let me first write it. Okay, so for gas van der Waals equation, the fugacity coefficient can be estimated using the following relation. So this is basically the relation phi equal to e to the power bp by rt. Okay, so what is B? I will explain it later. Phi is the coefficient of fugacity. Okay, so this is for a van der Waals gas. This is the relation of the fugacity coefficient with this pressure, temperature, and B I will explain. So P is basically is the second real coefficient for the van der Waals gas. Okay, so I will explain how this second real coefficient comes. P is the pressure of, I mean the true pressure actually. That means the pressure of the pressure in the ideal case. Okay, so true pressure, and for our problem the true pressure is 10 atm, right? So we write true pressure, that is 10 atm, temperature is 20, temperature is what, temperature is 25 degrees centigrade. So 25 degrees, and that means it's 298 Kelvin, and R is 0.0821 liter dot atm by mole Kelvin. Okay, this informations all are given. Okay, so now let me explain what is the second virial coefficient. Yes, okay, so now you can basically write this. So let me write it once again. For van der Waals gas, P plus A by V square into V minus B equal to RT. Right now we have to basically expand these things. Okay, so P will be equal to RT into V minus B minus A by V square. Now you can take V as common, so RT RT by V into hmm, so RT into, if you take V common, then this will basically be 1 V by V inverse minus A by V square. Now if you just do the binomial expansion, this will give you RT 1 minus 1 plus B by V plus B by V square plus dot 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 dot, lot of terms are there, right? Just P. Now you can write it like this. So mm, mm, now you can write P equal to RT plus B minus A by RT into V, similarly B square by V square. If you can write it like this, right, after doing the expansion and all. So this so RT, so this is basically the first virial coefficient, this is the second virial coefficient. Okay, sorry, this is V square, 1 second. So just let me write it 1 second. RT plus RT plus P minus. Okay, so like this. Okay, so now here this coefficient RT, so after doing that, so 1 by V, so okay, 1 by V. So here this basically is the P minus A by RT, is basically is the second virial. There are a lot of higher order terms, so we're neglecting that. So this is the basically the second virial coefficient. Okay, so in this case B will be equal to P minus A by RT. Now for the problem that we have, this we can approximate the B value equal to this constant B. We will, for the timing, we'll consider this second term. Okay, the reason is like in the problem also, like the A is not given, right? This other that pressure correction term is not given, only the B is given, right? So for the time being, or that's why for the time being, are considering this A part. So the B, the capital B will be approximated to the constant small b. Okay, so now so let me just write the values now. Okay, so B in this case would be equal to 3.707 into 10 to the power minus 2 liter per mole. So now in this problem, this is the phi. Okay, so you can write this thing like this, right? If you take log on the both sides, so it will gives you ln phi would be bp/rt. Now ln phi would be gives you bp. Substitute the value of b, 3.707 10 to the power minus 2 into 10 by 0.0821 into 298. This will give you phi equal to e to the power 0.01513. That gives you 1.0152. If you calculate this, you will get phi as this. Now phi is means the coefficient of fugacity, right? Now from this coefficient of fugacity you have to calculate the actual pressure. So the effective pressure F is phi into P, right? Phi you have calculated 1.0152. The true pressure was 10 atm, right? Here in the question 10 atm. Okay, 10 atm. Now if you write it like this, this will gives you basically into 10 atm. So that basically gives you 10.153 atm. This is the F. So the correct answer will be this one, 10.1. Okay. I hope you understood the problem number 2. Now the problem number 3. So the problem number 3, the latent heat of fusion of deuterium at 18.56 Kelvin is 47 calorie per mole inverse. This is the latent heat of fusion for deuterium. The slope dp dt is equal to 40.5 kg per centimeter square per mole inverse. Now the difference between molar volume of solid and liquid deuterium at this temperature is what? So this is basically you have to find out, and there is one information given, that is 1 calorie is equal to 4.184 joule. Okay, so the options are option A 0.0625, option B is 0.026, option C is 2.669, and option D is 0.26. So these 4 options are given. So the question is, let's just first read the question once again. Okay, so the latent heat of fusion is given at this Kelvin. For this deuterium is 47 calorie, and the slope is dp dt. So latent heat L is given at a particular temperature. The slope is given dp dt, and you have to basically find out What is the difference between molar volume of solid and liquid phase of deuterium? So fusion means what? Fusion means uh, liquid will be transferred from the to the solid, right? So 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 it's- hmm. So now to solve this problem, we have to use the Clausius-Clapeyron's equation, because this problems deals with the phase transition, right? Phase is transferring like between solid state to liquid state, right? So that's why, like, because of that, the heat of fusion is given here at a particular temperature, and dPdt is also given, so we can easily use the Clausius-Clapeyron's equation, right? So let me first write the expression of the Clausius-Clapeyron's equation. So the okay, so what is basically the Clausius-Clapeyron's equation? So let's suppose the Clausius-Clapeyron equation is relates the rate relates the relates the change in pressure P with respect to the temperature, right? T during phase transition. Okay. So during the phase, so Clausius-Clapeyron's equation basically gives you that during a phase transition, if you change the pressure, what will be the change in the temperature? Because phase transition will happen at a particular temperature, right? Now at a particular temperature and also a particular pressure also. So both this pressure and temperature basically relates with each other. So if you change the pressure uh, during the phase transition, the temperature also will change. Okay, that also we have seen in experiments, right? So like if you change the pressure, that the transformation between the heat from the solid ice to liquid water also gets changed, right? I mean the transition temperature. So, okay, so like that here also, if you change the pressure, the temperature will also change. Okay, so now, so during this phase transition, okay, so so this pressure and temperature, how it related to each other? Okay, so this is basically related as by this equation, by this Clausius-Clapeyron's equation. Okay, so dp dt equal to L by T into delta V. So what is the different terms involved here? So L is basically the latent heat of the transition. Okay, L is the latent heat, and delta V is the change in molar volume. Okay, so this change in molar volume basically you have to calculate. Okay, so latent heat is given. So for our problem, so now come back to our problem. So for our problem, latent heat is 47 calorie per mole inverse. Okay, so let me just write. So latent heat will be L will be equal to 40 47 calorie per mole, but our answer we have to calculate in terms of joule, right? That's why this conversion between calorie and joule is supplied in the problem. Okay, so now this will be 47 into 4.184 joule per mole. Now if you multiply these two things, this will basically give you 196.648 joule per mole. So this will be the latent heat in terms of joule. Now comes the temperature. So temperature is already mentioned, like at a particular temperature, right? That is here 18.56 Kelvin. So T is basically, so the states are like from, it's basically from solid, from liquid, deuterium is converting from the liquid state to the solid state, right? So as the fusion is happening, so the temperature is quite low here, because that's the reason. So T is like 18.56 Kelvin. This is the T. Now delta we have to calculate. So let me just, dPdt is also mentioned here. dPdt is, what is dPdt is 40.5 kg per centimeter, kg per centimeter square into mole inverse by mole. Okay, so this is kg is this is written is at kg by centimeter square, but we need to write it in terms of pressure and temperature, right? So how can we do that? So for that I have to convert it into Pascal into Kelvin. Okay, so in order to do that, you have to first convert kg into dyne, and from dyne you have to convert in Pascal Kelvin. Okay. So 40.5 will be, now if you convert kg into dyne, you have to multiply it 980.665. This is basically, I'm just converting the things. So dyne per centimeter square per minute. Now if you convert it into Pascal Kelvin, then it will simply become 39716.93 Pascal into Kelvin inverse. So I have just convert the unit from kg centimeter square to Pascal in Pascal by Kelvin. Okay. This is the value of dPdt. So now, so from this equation, all of the values we have already calculated. Now just substitute all of these things into this equation basically. So now from this equation, and write this equation like this. Okay, here delta V will be equal to L by T into dP dt, right? We can write it like this. Now I have to calculate the delta. We just, in order to do that, just substitute all of the things. So L is like 196.648 in joule per mole. Next come the temperature, that is 18.56 Kelvin into dPdt is already 39716.93 Pascal per Kelvin. Now if you calculate, simply calculate, do all this calculation, you will be getting 0.000269 meter cube per mole. But in the problem, one second. So in the problem you have to calculate it in terms of centimeter cube, actually centimeter cube per mole. So how you can do that? So in order to do that, you have to convert this meter cube into centimeter cube, right? So for that, delta V will be 0.000269 2669 into 100 centimeter per meter cube. 1 meter is equal to 100 centimeter, right? So delta V equal to 266.9 centimeter cube. So this is 2.669 centimeter cube per mole. Okay. So the option for our system will be this, right? So the correct option will be option C. Okay. So the main thing is like you have to use the Clausius-Clapeyron's equation in order to solve this equation. Okay. So everything is given. Latent heat is given. Delta V we have to calculate. Latent heat is given. That is the the heat that is required for the fission process, that is mentioned here. Temperature at which this fusion is happening, that is also mentioned here. dPdt slope of pressure with respect to temperature, that is also given. So we'll substitute all of these things in this equation. Just convert the units according to your system, according to your answer, basically the options, and from there just do the calculation, numerical calculation, and get the answer. Okay. So this is our problem number 3. I hope you have understood how to solve this kind of problem. Okay. So this is the problem number 3 is now done. Now we'll go to the problem number 4. Problem number 4 is which of the following terms is not 0 when ideal two gases are mixed together. Okay. So the options are option A, delta each mix, option B is delta B mix, option C is delta G mix, and option D is delta U mix. So we have discussed like this in case of ideal gas, let's suppose these are the two ideal gases. Okay, suppose this is in a container, there is separation between the container. So these two sides of this two container, there is ideal gas 1 occupying the volume V1, ideal gas 2 occupying the volume V2. So now when you move this partition, so both these gas will mix. Okay, 1 plus 2, and the total volume will become V1 plus V2. And we have already discussed like in previous tutorial, also in the classes also, I think. So it already discussed, right? So during this mixing, the entropy of this whole system is getting increased, right? And this thing is termed as the entropy of mixing, right? So we have already got a delta S is increased like that, T ln V by V1, delta S1, delta S2 also at T. This is suppose V, this is V, then V by V2, right? Like this, and provided that this whole system is not in completely isolated from the surroundings. Okay, so basically there should be no change in temperature with the surroundings is happening for this case. Okay, so if you consider this kind of system and you mix two kinds of gas, in that case there will be a change in the entropy, and that is known as entropy of mixing, right? So hmm. And one more important thing that is noticed here, it's called ideal gas. Okay. So now what you have to do, now here in the problem it has been asked, what is the thing because of this mixing, what is the change that should become not zero? Okay, let first consider the delta H mix. Okay, so delta H mix, what basically delta H mix basically gives you the enthalpy of mixing, enthalpy. Okay, and for an ideal, enthalpy basically accounts for the dq, right? The uh, change in basically, if there is heat, if the heat is exchanged or transferred between systems or intermolecules, heat exchange is happening. In that case, if the system gets heat absorbed, or uh, it will emit heat, in that case there will be a finite value of delta H mix. But here the gases are ideal gases, right? So although if you see ideally, I mean if you see realistically, actually if you move this uh, barrier, when basically two gases mix with each other, when you move this barrier, so realistically this gas should collide with each other more, and it will basically gives you more kinetic energy. So the heat will getting increased, but that is in realistic case. But here in the ideal case, what happens, this we didn't consider this intermolecular force of the gases, right? So for that reason, as in the question itself, it's mentioned as an ideal gas. Okay, so as there are no intermolecular forces has been considered for this problem. Okay, so there should be no heat that has been generated if you mix those two gas. Okay, so considering all this fact, so the delta, there will be no heat exchange will be happening because of the mixing. Okay, so that means the delta H, that means the enthalpy change for this mixing will simply become equal to zero. A similar case, next things comes the delta V mix. Now for delta V, so for delta V, what happens for delta V? Delta V basically is the volume. Okay, so the volume should remain unchanged, right? The volume V1 plus V2 will be equal to V, right? So previously it was V1 plus V2, and after that it becomes V. That itself is V1 plus V2, right? So that becomes zero, right? Delta V mix will, anyway, by common sense also you can say it's zero. Next comes the delta G. Okay. Now delta G is, if you remember the expression of delta G, let me just write 1 second. Gibbs free energy, right? Gibbs free energy So Gibbs free energy is basically this, G equal to U plus PV, right? Now if you, this is the Gibbs free energy, right? Gibbs free energy. Now from here delta G will be delta U plus P delta V plus P delta P. Now delta U is here. What is delta U? Delta U is, we know from first law dq equal to delta U plus delta W, right? The delta W will be delta Q minus delta U minus delta W. Delta U is TDS, T delta S, right? T delta S minus P delta V. So delta G will be simply T delta S minus P delta V plus P delta V plus V delta P. So delta G will be T delta S plus V delta P. So this basically will be the change in Gibbs free energy. This is basically the change in the Gibbs free energy, okay, when you mix. So now this case, so now this case, this change in Gibbs free energy is equal to T delta. So this basically, what the reason for writing this equation is, you can see delta G is equal to T delta S. Delta S is basically nothing but change in entropy, right? In entropy. So for the fact that entropy itself is changing due to mixing, so from that we can easily conclude that delta G can also change, right? So delta G mix during the system should be not equal to 0. So now this should be the answer, but for the sake, okay, so now for the sake also, like delta U, if you see also delta U mix, now you see delta U mix. So what is delta? Delta U basically, if you CVDT, right? Delta is equal to CVDT, CV delta T. That is basically the change in temperature. Change in temperature. But for our system, there is no change of temperature is mentioned, right, in the problem. So for delta U mix is also equal to 0. So only thing that remains not 0 is delta G mix. Okay. So our correct answer will be delta G mix. That is option C. Okay. So problem number 4 is complete. So let me just explain it once again. So what the question is basically asks you, which of the following terms will become non-zero when two ideal gases are mixed. Delta H is enthalpy, delta U is the change in, delta V is the change in volume, delta G is the change in Gibbs free energy, and delta U is the change in internal energy. So basically there are two gases, 1 and 2, occupying the volume V1, V2. So when you move this barrier, these are like separated using this partition. So when you move the partition, these two gases mixed up. So because of that, you have already studied in the previous class, right? There is a term that will be involved here, which is known as entropy of mixing, and for that there will be a change in entropy for the system, delta S1 and delta S2. That is the change in entropy for gas 1 and gas 2. And this fact, why you are using this fact, because this actually helps us to determine whether which of this option will become not equal to 0. This fact will be helping us in order to like determine that thing. Okay, so first we have considered delta H mix. So delta H mix basically gives you the change in, if there is like heat is involved in the system, like if you mix two gases, if there is new, if like what happens if if like heat is absorbed or released because of the mixing, in that case delta H mix will be not equal to 0. But here we have considered ideal gas, so if we mix this, we have not considered the intermolecular pressure or something like that, as it's ideal gas, so delta H mix will simply become 0. Similarly, delta V mix will be also become 0, because if two, like the volume at final initial stage both are equal, so delta V mix will equal to 0. And delta U mix also, this delta U mix, you know, is CVDT, that means the change in temperature. So during this mixing there is no change in temperature happen, so delta U mix is also equal to 0. And the things that that option that remains is delta G mix. So delta G mix is basically depends on the change in entropy and change in pressure. We already know there is change in entropy happens here, right? So if there is change in entropy happens, the change in Gibbs free energy also happens. Okay, so from that fact we can surely state that delta G mix would be not equal to 0. Okay, so the correct option will be the option C. Okay, so this is the way to solve this problem. Let me just check. Hmm. Okay, so I hope you all of you understood how to solve this problem number 4. Okay, now we'll go to the problem number 5. Standard standard chemical potential of oxygen at 300 Kelvin is given by 10 kilocalorie per mole. Now the volume, because of this this chemical potential of oxygen is given. Now the volume is decreased to 2.46 liter isothermally, and the increase in free energy is 1.342 kilocalorie. Now the fugacity of oxygen is what? 18 we have to complete. Okay, let me also write down options. Option A is 9.5, option B is 1.0, option C is 5.46, option D is 7.87. These are the all four options are given. Okay, so basically before going to the problem, let me just briefly tells you some important facts about the fugacity and like the other thermodynamic potential, like how these thermodynamic potentials are related to the fugacity. Okay, so in the problem you can see there is two things. One is the chemical potential is there, And next thing is this change in this change in Gibbs free energy is also given. Okay, so basically fugacity itself is related with the change in the chemical potential. Okay, and change in the chemical potential is also related to the Gibbs free energy. So basically we have to like use these relations to interchange these quantities with each other. Okay, so how to do that? So as I've mentioned that fugacity is related to the chemical potential mu. Okay, and for a pure substance, for a pure substance, this mu is also related with Gibbs free energy. Okay, now how it's related? So basically related like this: d mu equal to dg m is equal to, and dgm already, dgm I'll explain what this dgm thing, how this m in suffix is coming. Sn dt minus vm dp, that we have already discussed here, right? This expression, I've already written. So m comes because gm sm vm is equal to quantities per mole. Okay, so that's why the m suffix comes. Okay, uh, so now what we can do now in this problem, uh, the system is remains at a constant temperature dt, right? So this term will become 0. So for this problem dt was remain at 0, right? So basically you can write d mu as vm dp. Now vm is, you can vm right, you can vm right p vm equal to rt, because vm is v by n, right? So n comes to this side, this becomes vm. Okay, so vm equal to rt by p. So just plug it in here. So d mu will now become to rt by p into dp. So now if you do the integration, what will give you? Mu minus mu 0 basically gives you, if you do the integration, suppose mu 0 to mu, p 0 to p, so mu minus mu 0 gives you rt. If you do the integration, dp by p, it will gives you log, natural log, so rt ln p minus p0, right? Okay, p minus p0, so ln, you can write it like the p by p0. You can write minus in log as a, inside a log as a division term, right? So this is it. Now here we can write it in terms of pressure, but we have another thing that is similar to the pressure, which is known as fugacity, right? That we have termed as fugacity, or you can call it as effective pressure. Effective pressure, if you consider like all of the volume of the gas and also the intermolecular forces that we have not considered in case of ideal gas, if you consider all of these things, the effective pressure of the gas will change from its original pressure, I mean true pressure, that comes from the ideal gas equation, and we have termed this effective pressure as fugacity, right? So instead of writing this change in mu, change in chemical potential mu in terms of true pressure, you can write it in terms of fugacity. So that can be, so now you can write it like this: mu minus mu 0 equal to RT ln F minus P0. Okay, F is the fugacity here, and I've already discussed, right? F is phi into P. Phi is the coefficient of fugacity. Okay, so this is it. So now comes back to a problem. Okay, so we have to for our problem we'll basically we have to use this relation. Okay, so basically just rewrite this equation: mu equal to mu 0 plus RT ln F by the T0 write as F0. F0 basically is the standard fugacity. Let's suppose it's 1 atm or something like that. Okay, like ATP, NTP case. Okay, which anyway would be constant for a substance, for a fixed substance. If you don't change the substance, the F0 will be remain same. Well, this basically is a constant. So what is the information is given? Okay, question. mm, Now in the question, the volume is decreased from initial volume. There is a change in volume. Okay, okay. So let me just write. So mu 0 at 300, mu 0 basically here we can consider mu 0 as 10 kilocalorie, kilocalorie per mole. That is standard at T equal to 300. At T equal to 300. V2 is the final volume, that is 2.46 liter, and change in Gibbs free energy or the normal free energy is 1.342 kilocalorie. Now change in mu can also write in change in delta G, right? So delta G will become delta mu, that is also 1.342 kilocalorie. Now the system expands, right? The volume decreases. System basically not expand, it will contract. Okay, so mu1 initially, let's suppose its entropy was initially at chemical potential initial as mu1, now it decreased to mu2. So delta mu was mu2 minus mu1 equal to mu2 expression you can write mu0 plus RT ln F0, and mu1 you can write it minus mu0 plus RT ln F1 by F0. So F1 F2 basically gives the, what is the F1 F2 basically is the fugacity at that particular case. Okay. Hmm. So volume is changing. Okay. Fugacity will be that particular state corresponding effective pressure, right? So now delta mu, so like if you do the thing, delta mu will be simply equal to mu naught will equal to f naught will cancel, so RT ln f2 by f1. Now here one important thing is there. Hmm. So okay. Hmm. So now so f2 by f1 we can write it as p2 by p1, right? Or p2 by p1 we can write it as v1 by v2, that is, that comes from the Charles law, right? Charles law, p1 v1 equal to p2 v2. Okay, now what we can do, we can just substitute delta mu. Already know delta mu is delta mu is 1 point, delta mu is 1.342. okay, so now we can write it like this: delta mu by RT equal to ln v1 by v2. v2 already know, right? So now we can write it like this: v1 would be equal to v RT. So RT value we have to basically substitute. R is, you already know, T is 300 Kelvin. Okay, and sorry to write it like this: v2 is 2.46. So v2 into e to the power delta mu by RT, right? v1 will equal to 2.46 into e to the power delta mu is 1.342, 1.34 1.342 kilocalorie by RT. So R into T 300 Kelvin. Now if you do all the calculation, you will be getting V1 as 23.34 liter. Okay, so V1 by V2 have already calculated, right? That is 23.34 liter to 2.46. Then V1 by V2 is itself equal to F2 by F1, right? Now F2 by F1, now what is the value of F1? You can see here one term is important: standard chemical potential and oxidation. That unit is this. So standard means initially. So standard chemical potential means what? Standard means pressure is standardized to 1 atm, right? That basically signifies the standard case, right? 1 atm pressure. So we can approximate F1 equal to 1 atm. Now if you put it here, F2 equal to 23.34 into 2.46 into 1, so that basically gives you 9.488, the value of F2. If you check the answer, we have an answer here, you can see 9.5. So this basically gives you the correct answer, that is 9.488. This is in ATM, right? Okay. So the main thing is how do you calculate. So many things are like related to each other. Okay, so you have to use all of this relation in order to calculate the final answer. So let me just briefly discuss it once again what I have done. So the problem itself, it's mentioned the standard chemical potential of oxygen at 300 Kelvin is given by this. The volume decreased to 2.46 liter isothermally, and the increase in free energy is this. Fugacity is have to calculate. Now the first thing is there is change in intensity, so change in free energy. Okay, and fugacity is related with the change in chemical potential, and chemical potential is also related with the change in free energy. So that means the change in free energy will be also related with the fugacity, right? So how to do that? So first, I have written the change in chemical potential in terms of change in free energy like this, and from there I have done all this calculation, and I have just established this relation, how this change in chemical potential is related with the fugacity. This is the final relation. Mu is the initial, mu is the final, and mu naught is the initial chemical potential. F is the final fugacity, F naught is the initial. So for our problem, uh, the standard chemical potential is given. Okay. Uh, so this is basically, so there is a T at 300 Kelvin, so T is given. Okay. So V2 is given, that is after the contraction the volume decrease, so V2 is also given. So so we first write all these things here, V2 delta G, and from delta G we have calculated for the delta mu, and from that we have write this expression, and F2 F1 we can basically nothing but the effective pressure, so it can be at P2 by P1, and P2 by P1 is again write as V1 by V2 from Charles law. Substitute all of this thing here, and which basically gives you the value of V1. Okay, the V1 would be simply this into this, so this V1 value will be 23.342. Now V1 you know, V2 you know, so if you just divide it, it will gives you 23.342 by 2.46, and that is basically also equal to F2 by F1, right? So this is we already know. Now F1, what is the value of F1? F1, if you read the question carefully, standard chemical, standard means it's things are happening on 180. Okay, that's why like STP. Okay, so for standard case we can consider F1 close to 180, as it's mentioned, it's a standard case initially. So F1 should we can equate to 180. Now just substitute F1 here. F1 into this will become, we will give you F2 equal to 9.488, which is the correct answer is option A, 9.5. Okay, so so this is basically is the procedure how to solve this problem. Okay, so if the all these things are given, potential, chemical potential, volume change. Okay, so how from that how can you calculate the fugacity? This is basically the main thing is is actually the way how you can calculate, like in few future problems also. Okay, so now we will do the next problem, which is the problem number 6. In the absence of any phase change, the change in entropy when the system is heated from T1 Kelvin to T2 Kelvin at constant pressure is given as, so option A is this, delta G1 by delta H1 by T1 minus delta G2 delta H2 by T2. B is Cp ln T2 by T1. So option C is Cp T2 minus T1 by T2 T1, and option D is mu1 by T1 minus mu2 by T2. Okay, so let's read the question once again. So in the absence of any phase change, so there is no phase change happening here, change in entropy when a system is heated from T1 to T2 at constant pressure is given as this. So to solve this problem, basically need the first law of thermodynamics again, that is delta Q equal to delta U plus delta W. Now during this process, as there is no phase changes happening, so let me just before stating in that, just write the expression. dq is basically TdS, TdS, delta U is basically Cp dt, delta W PdV. Okay, so as during this process there is no phase transition is involved, so that means there will be no volume change. If there is no phase transition, then simply no volume change will be there, right? So this term will equal to 0. So TdS will be Cp dt. Now Ts will be Cp into dt by T. Now then the problem, it asks that the temperature is heated, that means this term should exist from T1 to T2. Then what should be the change in entropy? So we have written the change in entropy in the differential form. Now if you integrate it, we will be getting S1 to S2 will be ds will be Cp T1 to T2 dt by T. So now this will gives you S2 minus S1 will be Cp ln T2 minus ln T1. Cp ln T2 by T1 is S2 minus S1, right? So the correct answer will be change in the entropy. The correct answer will be which one will be the correct answer? T2 by T1. This will be the correct answer, right? Okay, so let me just explain to once again what I've done. So in the problem is stating that if there is no phase change during a process, what will be the entropy change if the system is heated from T1 to T2 at a constant pressure? So what I've done, I will first write the first law of thermodynamics, and as there is no phase change is involved in the system, so dW PdV will become equal to 0, as dV will be equal to 0 as there is no phase change, and from there TdS Cp dt, so ds you can write is Cp dt by T. Now this is a differential form. Now if we integrate it from S2 to S1, so Cp dt will give you ln T, right? So S2 minus S1 equal to Cp in ln T2 minus ln T1. So S2 minus S1 equal to Cp into ln T2 by T1. So this is basically will be the change in the entropy because of this whole process, and the correct answer will be the option B, right? Yeah, the option B. Okay, I hope all of you understood. So So the assignment is concludes here. So still we have around 25 minutes left. So for that we can like discuss some extra problems, right? For this 25 minutes. Okay, so we'll discuss some extra problems. Let's see how much we can cover. Extra problems. So problem number 1, let's suppose two identical containers, one filled with 1 mole of an ideal gas at 500 Kelvin, and the other with 1 mole of the same gas at 300 Kelvin. Now these two containers are connected via a valve, okay, in an insulated enclosure. So basically that means insulated enclosure actually signifies that there is, for external surrounding, there should be no heat comes into the system or no heat goes out into the system. This insulated enclosure basically denotes that thing. Okay, now the gases are allowed to mix and each reach thermal equilibrium. Okay, now the problem is find the total entropy change due to the mixing process. So the entropy of gas mixing basically, but here you have to calculate in terms of temperature, not volume. Okay, so what happens here? So basically, so there will be change in like due to the volume also there will be change in the entropy. Okay, but for the case we will only consider the change in entropy due to the temperature, because the volume is not mentioned in the problem. Okay, so uh, we will only consider the entropy that is changing due to the change in temperature. Okay, so the answer is, now first what I have to do, uh, the final temperature you have to calculate, right? Like it's suppose like two liquids at different temperature, like is mixed with each other, they will, one is like, let's suppose a bit hot, one is a bit cold, then by thermal equilibrium it will reach a final temperature, right? Similarly for this gas system also, when two gases are mixed it will reach a final temperature. So that is the heat that is uh, like that is exerted by one gas will be uh, absorbed by the other gas, right? So so Q1 delta Q1, that is the heat that is emitted from one gas, will be absorbed by other gas. Okay, So NCV, let's suppose this is the gas with the high temperature. I mean, yeah, so high temperature gas will lose its temperature, right? 500 to TF final, and lower temperature it gain its temperature, right? TF minus 400 to 300. So TF will be basically 800 by 2, that gives 400 Kelvin. Final temperature will be 400 Kelvin, right? So now for the both the gas, what happens? Because the temperature is changing, there should be a change in entropy. Okay. So for the gas one, delta S1, NCV, ln T final into T initial. This is the entropy change. Let's suppose for a system, if the entropy changes, the temperature changes, right? This is the relation between the entropy and the temperature change, right? So delta S1, delta S1 will be NCV ln TF is 400, TI is 500. Similarly, delta S2 will be NCV ln T final is 500 by 400 by, here it was initially 300. So this is the entropy change due to the temperature. Okay, delta S will be delta S1 plus delta S2. So that will be CV into ln 400 by 400 and 500 plus CV ln into 400 by 300. So this basically gives us CV ln 400 square by 500 into 300, and gives you CV into ln around 1.0667. Okay. Now for an ideal gas, you can, for a monoatomic gas, monoatomic ideal gas. Okay. If you can calculate, you can take CV as approximately equal to 5 by 2 R, right? I substitute as 5 by 2 R to ln 1.0667, so that basically gives you around 0.16 R. This is the delta S. Okay. R is the real ideal gas constant. Okay. This is how the entropy will change during this whole process due to the temperature change. Okay. This is one problem. Okay. Basically, okay, so that's it. Now let's discuss another problem. Problem 2. Thermal power plant operates between a hot reservoir at 900 Kelvin and a cold reservoir at 300 Kelvin, right? Now the plant produces 500 megawatt of power. Then you have to find out what is the maximum possible efficiency of the plant, and next thing you have to calculate how much heat must be rejected to the cold reservoir per second. So the thermal plant, this is suppose a thermal plant P. It operates between a, this is a hot reservoir TH and a cold reservoir, right? The hot reservoir TH is at 900 Kelvin and the cold reservoir TC is at 300 Kelvin. Okay. Now this what basically it does, this power plant draws power from this hot reservoir, do some work, then during this procedure it will like lose some of its energy that has been drawn out from this hot reservoir, and after doing the work the rest of the energy will be supplied to the cold reservoir, right? So Q1 heat is collecting from here, Q2 is supplied from here, so W will be equal to Q1 minus Q2, right? So you remember, right? So from this diagram you can easily figure out this power plant is basically act as a Carnot engine, right? And the work done now, the work done is here Q1 Q minus Q2 is also 500 megawatt. Okay, now what is the things you have to find out? So first thing what you have to find out, what is the maximum possibility efficiency of the plant. So as the power plant is working like a Carnot engine. So for the Carnot engine, as it's equivalent to Carnot engine, you can use the formula that is used for a Carnot engine, right? And one of the important thing for a Carnot engine is its maximum efficiency eta max will equal to 1 minus T equal to T hot. Now for this case 1 minus 300 by 900, so 1 minus 1 by 3, that gives you 2 by 3, so the efficient will be 0.667 eta max. This is the maximum efficiency. Okay, so we got the maximum efficiency, and you can use this maximum efficiency actually to calculate the other quantities also. Okay, So what is the first quantity that you have to calculate? So the first quantity is the work done, right? So eta, you can also write it like this, right? Eta equal to work done minus q. Q input, that means q at high temperature, that the q temperature that you get, that is getting inputted. Okay, so work done is already 500 megawatt, and qt you have to calculate, that is the heat. Okay, qt and qc, right? qh, let's write it qh, like hot denote as h, qh. Okay, so now qh would be 500 by 0.667. qh basically would be 750 megawatt. That would be the heat that has been drawn out from this hot reservoir. Okay, this is one thing. Now the next thing is you have to calculate what is the heat that has been rejected to the cold reservoir. Okay. Now in order to calculate that thing also, you can calculate work done is already defined, right? Work done is 500 megawatt, right? So work done is basically qh minus qc. So qc will be basically work done plus qh. Work done is 500. Sorry, I think I've done a mistake. Sorry, q cold would be qh minus work done. So qh will be 750 minus work done is 500. So this will be to 250 megawatt. That is the heat that has been rejected to the cold reverse reservoir, right? So basically this pump is acting like a Carnot engine between two reservoir, hot and cold reservoir, and the temperature of this both two reservoir is mentioned in the problem. That is, for the hot one it's 900 Kelvin, for cold it's 300 Kelvin, and during this whole procedure this plant is producing 500 megawatt of power. Then you have been asked to find out what is the possible maximum efficiency of the plant and what is the heat rejected. Okay. So first as it's a Carnot engine, so for a Carnot engine you already know what is the maximum efficiency of a Carnot engine. That is eta max will be 1 minus Tc by Th. So by using this formula we have calculated the maximum efficiency, that is 2 by 3. Okay, that is 2 by 3, that we have already calculated. And similarly, so here we have used, so by this formula we have calculated the eta max, that is 0.067. And as we know the eta max, we can also use the eta max to because we already know this thing, right? We can write it like this, right? Eta is equal to 1 minus T2 by T1 is equal to 1 minus Q2 by Q1, right? Now we can write it Q1. Q1 is basically heat input and Q2 is heat output, right? You can write is Q1 minus Q2 by Q1. What is Q1 minus Q2? That means the heat rejected because the system is itself doing some work, right? So because of that there is some heat that should be rejected, right? So that is mentioned here as QH. Okay, so that is Q1 minus Q2. So this basically gives me the work done, and Q1 means the heat input. So this same relation I've used here. Okay, as you can see, work done by Q heat input. Okay, so work done is already mentioned here in the problem. So what is the work done? So work done is basically here is 500 megawatt. This is the power. Power means the work done in what it is mentioned. So means there is a like the rate is also defined by time, and also like the heat. So everything is like changing with time. There is a rate involved here. So work done by per unit time basically gives you the power. So that's why it's written in watt. So anyway, so all of these units will be calculating as a unit of rate. Okay, so this includes by T, this includes also by T. That means so Q, what the Q, the thing, the Q that is calculated for here also basically gives you the rate of heat. Okay, because this includes time, so this also includes time in order to non-dimensionalize the eta. Okay, so 500 megawatt. So from here, if you like eta max, we have already calculated, that is 0.067. Now just substitute that 500 by 0.067 here. So basically that will gives you KH equal to 750 megawatt. Okay, this basically is the uh, this basically is the heat rate that is comes from the hotter side. Okay, now next we have to calculate the work done. Next we have to calculate the hot that is rejected to the colder reservoir. So for in order to calculate that, we know the work done, right? Work done is QH minus QC. That means that basically the heat reject, the rejected heat basically act as work, right? So W is basically QH minus QC. So QC we can write is equal to QH minus W, and QH value already know is equal to 750 and minus 500. So basically gives you if you divide 750 minus 500 is equal to 50 milliwatt. But this is basically the heat that is rejected to the colder reservoir. So this is the end of the problem. So that's it. So basically we have learned a lot of things in this tutorial. So first thing that we have learned is the triple point. So triple point basically is where all the thermodynamic phases like gas phase, liquid phase, and solid phase coexist with each other. So what had this is at a thermodynamic equilibrium. So what will be the basically for this selenium problem? So what would be the pressure and temperature for in order to get the triple point? So that pressure and temperature we have calculated in the first problem. And second problem we have like got a new concept of this fugacity thing, which is basically is pressure actually. But if you consider in a realistic system where like you consider like the pressure in the like the intermolecular forces, the volume of the atom, all of these things, if you consider, it will definitely deviate from the regular pressure term, right? The regular pressure term means that pressure that is used in ideal gas, that should change, and that changes the changed pressure or the effective pressure is termed as fugacity. So how this fugacity is there, this coefficient of fugacity, and from there we have calculated the actual fugacity. So this is one problem. Next we have done a problem of Clausius-Clapeyron's equation. Okay, like where by using dp/dt slope, the change in latent heat and temperature, we have calculated the delta V, that is the change in the molar volume. This is one type of problem we have done. Second thing we have calculated, we have like used this like the entropy, like when two gases are mixing with each other, what are the things that will be changed and what are the things that will be not changed. Like here you have to figure out that delta H enthalpy, that thing basically doesn't change, but delta G that incorporates the change in entropy, that thing is changing because two gases are mixed with each other. But like this we have like discussed many different types of problem during this tutorial. So hope this tutorial helps you a lot in order to get a good understanding on the topic. So this is it. Thank you.